Gentlemen, I will talk about a more industrial approach on this theme. I'm from HPS, located in Munich, and we're a company in the space business and build antennas for satellites. So, I will describe a little bit the antenna itself, some short words for the optical measurement, because it was done under certain circumstances, and then we'll show how this methodology described before does work. In the end, of course, some summation and then an outlook on our next steps as we want to conclude with this methodology. Well, first, what's about the thing we talk about? It's a so-called Earth deck antenna. It's a full CFRP antenna in an RF band called QV and KA band. It's a sort of frequency, especially the QV band. It's about 40 gigahertz, and there you need a very tight accuracy. For example, the RF guys usually look for the RMS of the surfaces, and then you have to have an RMS of about 20 or 30 microns. So you have two very important things. Of course, in space business, you have to have a very low mass. On the other side, you have to have a very high stiffness, and you have to withstand the launch loads. So it's a quite complex simulation on this thing, and on the other hand, many of the loads you can't get on an experimental way on Earth. You can imagine a whole circle around the Earth you can measure in space, and you have to simulate it, and therefore you have to have the assurance that your simulation is fine. So, nevertheless, besides simulation in the space business, there will be done a lot of testing. For example, for this antenna, you see, we did vibration tests, sine and random in all axes. We did thermal tests in the thermal vacuum chamber. We did acoustic tests in an acoustic chamber, and for sure, as it's an antenna, we have to do some RF tests to choose the quality of this antenna. In this things, we will have a look on the TV chamber, because under those different temperatures the antenna will deform, and measurements in this thermal terms are relevant. As you know, if they are in space, there are no gravity loads or things like this, but there are thermal loads, and they will deform our structure. As I mentioned, we have to have a very high accuracy on our surfaces, and therefore we had to do these measurements with an optical system. And with an optical system, this has an accuracy from about 2 microns or something like this, and therefore we took an EPC system. It's a speckle interferometer process. So the principal way how this measurement does is to take a pulsed laser and do a speckle pattern, and then you put the interferogram between 2 pictures, and when counting the lines you can, according to the wavelength of the laser, recalculate the deformations. Another thing what's of course of interest is we have to do the measurement under those extreme conditions. It's the vacuum chamber, and there you have to put a special window which that the laser, which you can't put into the system, can illuminate the interesting surface. Now, what we done then is we did, that's quite usual in space business, some cycles under vacuum, in this case between -120 and plus 120 degrees Celsius, and during one cycle we did the measurement. And as I mentioned before, this speckle measurement is a summation of all those deformations done for every pulsed measurement. There were some challenges, of course. If there are too big movements, then you have to increase your pulse rate, and therefore we had to look for minimize the rigid body motion. So even this jig in the chamber had to be made of CFRP with low CTE to reduce the deformations as much as possible. On the other hand, you can imagine if we are in this high accuracy of measurement, any vibration which will have an influence on the movement of the reflector will decrease your measurement accuracy. Well, in the end, we got it, and we did, in addition, of course, the thermal analysis. Of course, if we do, once again, those single point comparison for the temperature behavior all through one of these thermal cycles, you get quite nice correlation, and you can say, well, this should be the thermal field. You apply on your model and calculate your deformations. Well, and then you get something like this. First of all, due to the optical restrictions on the chamber, on reflections and so on, we had to cut some data area so that this was the remaining measurement. And of course, we do have the full picture in simulation. And without these full-field comparison, you usually try to take a typical line and compare these deformations. This is the measurement, and this are different simulations. Of course, we do have uncertainties in our model, especially on those things as different CTEs. And in the model, for example, you have, of course, the thickness of your bonding film is usually always the same. In reality, if you have those curved surfaces, and so they may change a little. And you can see in these two pictures just a little change in the bonding thickness, which more or less inside the manufacturing tolerance. So you did this and compared it to the measurement, and it says, yes, this model is quite fine as inside the different possibilities of deformation, our measurement is there. But this is something of choice, more or less. I do not know what happened if we took another diagonal or things like this. In the end, we only compared two lines of measurement and two lines and simulation. George did announce these things where the process is described, so I will jump over. What we did now is to define, first of all, our region of interest and went through the process. So we decomposed this one and decomposed this one, and then reconstruct the picture. Of course, as mentioned before, you have to take these decomposition and reconstruction of the pictures with the same base and with the same amount on polygons, and then the result is quite similar to things George showed before. We have those points which are compared the FE shape descriptors and the measured descriptors. Now you will say, hey, that doesn't work so well. And that's right. But you have to keep in mind these measurements were done some years ago, and the whole process wasn't adapted to these evaluation and validation of the process. So if you go back, for example, we plotted something and our region of interest was more or less guessed. So a most important hint on this things is you have to have, of course, as exact as possible, the same region of interest. If you change, your descriptors will be different. So if you slightly put this square on another side, the process will show bad results. Therefore, the other thing is that you have to have this in mind and then do it at the very beginning. If you plan your tests, you have to imagine and to plan how to define this region of interest. So, for an outlook, we will do the same procedure on a so-called dual gridded reflector, where we again have a full field measurement, this time not with the mentioned measurement method, but with a laser radar. And on this thing we will do, similar to this picture, reference points, which can be detected exactly. And we will do this also in our FEL simulation. So if we do have those reference points, then we can fix very easily the region of interest, so that we do not have some deviation of these regions, and we are very sure that when we can get these new data, we will have a very nice tool to validate our models, or them have much more security on all those other load cases. As you can imagine, again, it's a thermal theme. In this chamber, you only have a gradient from during your heating or cooling phase according to the different capacities. In simulation, for the orbit, we have to do many different gradients according to solar impact or not going into the eclipse. So when we can have the validation of our model according to the measurement, which we can on Earth, we have confidence that the product also will work in space very well. Thank you very much.